So we are going to remind ourselves what is a solution. Well, a solution is a homogeneous mixture of our solute and our solvent. And that's great if you know what homogeneous mixture is and you know what solvent and solute are. By the way, can everyone hear me? I know I always think that, and then it's too late. Yes, okay, good. So a homogeneous mixture is where the solute and the solvent are evenly mixed at the particle level. So there are no clumps of either material. So you shouldn't be able to see any areas that look like just one thing or just the other thing. And let's just remind ourselves about solute and solvent. The solute is the component of the mixture which is present in the smaller amount. So if you had salt water, that would be your salt, would be the solute. And the solvent is the component which is present in the greater amount. So again, if you had salt water, that would be your water. All right, we're going to take a look at a few pictures here. I will post this file later so that you can actually have it for your own reference. Which of the diagrams to the right shows a solution? Is it A, B, C, or D? So the first thing we want to do is we want to think a solution. In order to be a solution, you have to have a mixture of two substances. Okay, so for A, every single particle is the same as every other particle. Therefore, that's just one type of substance. So A is a pure substance, not a mixture. Okay? So A is not a solution because it is not a mixture. Okay, how about B? Well, in B, we can see that there is one type of substance here, and there is a second type of substance here. So we have a mixture. So B is a mixture. But the second thing we need to know about a solution is homogeneous. And remember, if something is homogeneous, there is even mixing. There's no clumps. Here, we have a clump of the sort of longish molecules. And here, we have a clump of the sort of Mickey Mouse looking molecules. And so that would not be a homogeneous mixture. That would be what we call a heterogeneous mixture. So a heterogeneous mixture has clumps. There's not even mixing of the two substances. Let's look at C. Okay, so for C, I see two different types of particles. I see the kind of ones that look a little bit like Mickey Mouse. Okay, they're all over the place. Yeah. But I also see some different molecules that are a little bit bigger. Yeah. So here's one that's a little bit bigger, and here's one that's a little bit bigger, and here's one that's a little bit bigger. Okay, so I do have a mixture, So C is a mixture, and it is evenly distributed. And I know sometimes people think, oh, don't I have a clump right here? Well, two molecules doesn't actually make a clump. We are limited in that we can't draw a really nice picture of billions of molecules. If you had a picture of billions of molecules, it would become really obvious that two molecules is not a clump, right? But because we're limited to what we can have on the screen, it looks a bit like a clump, but if you can sort of wrap your head around that, um, if we only have a couple molecules together, that doesn't qualify as a clump. So this does have even mixing. So it is homogeneous. And that means it is a solution. Mhm. And then finally, if we look at D, we see that every particle is exactly the same as every other particle. So D is not a mixture, it is a pure substance. And sometimes people look at A and they say, well, I have different kinds of particles there. You know, if I go back to A, I see red things and I see black things, but those are all part of the same particle. Every particle is the same as every other particle. What we have here is we have a pure substance. This particular one is a compound because it's got different elements within the particle, but there's no different particles. They're all one black with two reds attached. We have a different kind of pure substance down in D. Because every atom is the same as every other atom, we have an element. An element? No, an element. Okay, so that is the difference. So here we have two pure substances. One is a compound, one is an element. We have two mixtures. One is a homogeneous mixture, and one is a heterogeneous mixture. All right, question number 2 here. It says circle the solute particles in the solution shown to the right. So I'm actually going to erase all the circles I put on there. And you need to remember now, what does it mean to be the solute? Is the solute present in the greater amount or is it present in the lesser amount? You can answer that in the chat. Is the solute present in the greater amount or the lesser amount? Yeah, the solute is present in the lesser amount. So if we were to circle the solute, I can look and I can say, oh, look, I have Mickey Mouse, 1, 2, 3, 4, 5, 6, 7, 8 Mickey Mouses, but I only have 1, 2, 3 of those larger molecules, and therefore the larger molecules are the solute, and Mickey Mouse is the solvent. What is the identity, question 3, what is the identity of the solvent? You might be able to recognize it from the shape. There is a molecule that we all know very well that looks like Mickey Mouse. See if you can figure that one out, and you can type it in if you can figure it out. And while I wait, I'll sing the Mickey Mouse song. Do 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 do. Mickey-Mouse, Mickey Mouse. Mickey Mouse is the shape of a water molecule. Okay, it is water. I only did that because yesterday I sang the song and they were all very disappointed it wasn't going to make it in the video, or at least one person was and everyone else was too polite to say otherwise. Okay, water looks like Mickey Mouse. It always has an oxygen and two hydrogens attached. Okay, so if you see a molecule that looks like Mickey Mouse, that is water. So that's just the background knowledge that you're going to want. Some new vocabulary. An aqueous solution is a solution in which the solvent is water. So this is the most common kind of solution you'll come across. Salt water, the solvent is water. That is an aqueous solution. Sure, you can have all kinds of other solutions. In fact, the air around you is a solution. It is a homogeneous mixture of all sorts of different kinds of gases. You've got oxygen and carbon dioxide and tons of nitrogen. The air is a solution, but it is not an aqueous solution because the solvent is not water. When we're looking at solutions, we can measure their concentration. Something can either be concentrated or it can be dilute. And that is a measure of the amount, I don't know why amount is two words, why the amount of solute, it is a measure of the amount of solute per given amount of solution. So that's going to be amount of solute per amount of solution. And there are all sorts of different units that we can use for concentration. And on the next page, we'll look at a few of those. But the most common one we're going to use and the one we're going to focus on in grade 11 and 12 and probably first year university. Is it a conversion factor? Oh, yes, it is. Yes, absolutely. I'm so excited. I know, I'm weird. Okay, so one way we can express that conversion factor is as molarity, where we say the amount is going to be the moles of the solute, and the amount of solution is the liter of solution. All right, so let us go and take a closer look at units of concentration and molarity in particular. Quantitative concentration. Units for concentration. And you'll often see me abbreviate concentration as just either conc or conc with a little n up at the top. They can be, as long as we have some sort of amount of solute, we could have grams of solute per liters of solution. We could have milligrams of solute per milliliter of solution. We could have micrograms per liter. We could have moles per kiloliter, etc., etc. Okay, all sorts of different kinds of units. As long as we have the quantity of solute over the, and in this case it's going to be volume of solution. Now, you got to be careful because it's always going to be the amount of solute per volume of solution, and a solution is a mixture of the solute and the solvent. What concentration is not, it is not the quantity of solute per volume of solvent. Okay, so if we are looking at the volume of a saltwater solution, it includes the volume of the water and of the salt, because if you take water and you add salt to it, the volume is going to increase. You simply have more stuff, so it will have a greater volume. Okay, so concentration, quantity of solute over volume of solution, not per volume of solvent. So just watch out for that.
Miss Pence,
Yes,
sorry, I have a question. So
of course.
everything that is not a homogeneous mixture is not a solution.
That's correct. The word homogeneous mixture and the word solution are synonyms for each other. They mean the same thing.
Okay, thank you.
So a homogeneous solution is, or sorry, a homogeneous mixture is a solution and vice versa. They mean the same thing, versa. Whoops. They are the same thing. Can't draw today. There we go. Okay, let us now take a look at the star of the day, and that is molar concentration. Or, as it's also known, the molarity. Okay, the molar concentration is the moles of solute. So that's our quantity of solute over the liters of solution. So that is our quantity of solution. So molar concentration is going to specifically have the units on top of moles and on the bottom of liters. So we're not going to have milliliters or grams or anything like that. It is specifically moles per liter. Molar concentration is also known as molarity. Those are two words again for the same thing. And we can simply write it as moles per liter. And remember that that is moles of solute per liters of solution. Okay, and we're going to spend a little bit of time just getting used to all of our units. We can also write moles per liter is abbreviated as capital M. Okay, so the capital M actually means moles per liter. So if you see the capital N, hiding inside that capital M is moles per liter. And we pronounce this unit molar. Okay, so capital M is pronounced molar and it means moles per liter. So if we were to say, for example, the concentration of NaCl, concentration of sodium chloride, solution is 3.2 m. What that means is that we would actually say that as 3.2 molar. This is how to say it. And what it really means is that we have 3.2 moles of sodium chloride per moles of sodium chloride per liter of solution. So that's what it means. So if we write 3.2 capital M, we say 3.2 molar, and we mean 3.2 moles of NaCl per liter of solution. So if we were to draw ourselves a little beaker, in our beaker, we would have, if we had 1 liter of solution in our beaker, inside that beaker, we would have 3.2 moles of dissolved sodium chloride. Okay. Now, a few other little terminology sort of things. The concentration of sodium chloride, that's kind of a long thing to write out all the time. So instead of always writing out the concentration of sodium chloride, we can write the shorthand for it, which is to put square brackets around NaCl. And this means the concentration of sodium chloride. So we're going to do a couple problems finding our molar concentration and mainly getting used to the units and used to the square bracket notation. So, for example, we might have find the concentration of HCl. That's what square brackets around HCl means. When 0.26 moles of HCl are dissolved in 1.0 liters of solution. And remember, this notation here, square brackets around HCl, means the concentration of HCl. Okay, so how would we show our work for that? Well, we would say the concentration of HCl, and we would write it like this because we don't want to write out the concentration of HCl, it's just too long, is equal to the moles of HCl per liters of solution. And then we simply plug in our numbers from the question. 0.26 moles is how much HCl we have per 1.0 liters. And so our answer then would be, nice easy math here, 0.26 moles per liter, or we could write it as 0.26 molar. Remember that capital M reads as molar. Now, it's probably not a bad idea to write that we have 0.26 moles per liter of HCl or 0.26 molar HCl, because shortly in the future, next week, we're going to be looking at finding the concentration of ions if you have an ionic compound dissolved in solution. And so we want to specify what we have. All right, let us summarize that math there. So to calculate molarity, in other words, the molar concentration, we are going to use this formula. Molarity is equal to moles divided by liters. So this is a division. It's not a conversion, it's a division. You will be using molarity as a conversion factor, but if you're asked to find the molarity, you're going to do a division. Just like if you were asked to find molar mass, grams per mole, you did a division. If you were asked to find density, you would do a division, which would be the grams per liter. Just like that, molarity you do by doing a division. So capital M is the concentration. Moles, of course, is the moles of solute. Oh, yeah, no problem. Yeah. Thanks, Shawnee. Okay. Let's see, where was I? Oh, yeah. And we have liters is the liters of, is it liters of solvent or is it liters of solution? Liters of solvent or liters of solution? What's going to go in that blank there? Yeah, absolutely. That is liters of solution. Excellent. All right, let's try one more example here. Okay, calculate square brackets HNO3 when 2.8 moles of HNO3, nitric acid, is dissolved in 40 milliliters of solution. Okay, well, we have to remember that those square brackets mean find the concentration. Of nitric acid. And we know that we have 2.8 moles and it is in 40 milliliters. Now be careful, anytime you see milliliters, if we're working with concentrations, those must be converted into liters. because of course, molarity is moles per liter, not moles per milliliter. So we need to make sure that our unit is in moles per liter. So you can do the conversion from milliliters to liters. There's a couple ways to do this. You can either say, I know if I have 40 milliliters, I can simply move the decimal place 3 places, and that will give me my volume in liters. So that would then be 0.0400 liters. If you're good with moving your decimal, that's great. If you're not confident about it, then just stick with the old tried and true method of using a conversion factor. So you would have 40.0 milliliters times, and we want to cancel milliliters and find liters. And there are 1,000 milliliters in 1 liter. And we get 7.0. No, we don't get 7.0. What is wrong with me? We get 0.0400 liters. So either way, we're going to get our liters. And now we can find what the question was asking for, which is the concentration of HNO3. So our concentration of HNO3, just put it in square brackets to say concentration of, is the moles over the liters. We were given the number of moles. It was 2.8 moles. 2.8 moles. And we found the number of liters, 0.0400 liters. And we get 7.0. And the unit of concentration is molarity. Or, if you prefer, you could write it as 7.0 moles per liter. Either way is fine, okay? And if you wanted to, you could stick on the HNO3 there. Because we're only dealing with one species here, I'm not going to get too excited whether we have that or not. Okay.
Miss Spence,
Yes.
is there a way to do the conversion factors where it's like all in one equation rather
Sure.
than two?
Absolutely. Shall we see that? So if
Yeah,
you
could
want,
we?
yeah, for sure. So if you wanted to do it in one line, you could say concentration, oh, can't write today, of HNO3 is equal to the moles over the liters, and we were given the moles, so we can plug that in right away, 2.8 moles, and we weren't given liters, we were given 40.0 milliliters. But that's okay because we know that we can convert milliliters by canceling it, and we want to have liters on the bottom, so we're going to put liters on the bottom, and there are 1,000 milliliters per liter, and that will again get you your 7.0. The units you have left are moles per liter, and that's exactly what we wanted, moles per liter, or 7 molar if you prefer. Okay, let us do one more here. Find the concentration of ammonium chloride when 25 grams of NH4Cl is dissolved in 250 milliliters of solution. So here we go. concentration of NH4Cl. Anytime you're finding the concentration, you're going to be doing a division. So we are going to say I need to have my moles over my liters. And we're going to start by doing this in one line, and then if you want me to, I can show you how to do it like broken down into a couple steps. Remember that this is moles of solute. And what do I know about my solute? I actually don't know the moles. What I do know is that I have 25 grams of it. So I'm actually going to put my 25.0 grams NH4Cl on the top. And I'm going to put my liters on the bottom. I don't have liters, but I do have milliliters. So I'm going to put my milliliters on the bottom. And now we're just going to have to do some cancellation to turn grams into moles and to turn milliliters into liters. So let's do the math around that. Let's start by turning grams into moles. Grams are on the top, so we need to put grams on the bottom to cancel. We want to have moles on the top. The conversion between grams and moles is the molar mass. And happily, I calculated this yesterday. The molar mass of ammonium chloride is 53.5 grams of NH4Cl per mole NH4Cl. Okay, that means our grams are gone. And on top, we are simply left with moles, which is what we want. Hooray. On the bottom, we don't want milliliters. We would like to have liters. So let's cancel our milliliters. It's on the bottom, so we need to put it on the top to cancel out. And we want to have liters on the bottom. And we know that there are 1,000 milliliters per 1 liter. And when we do all of that, all we're left with on the bottom is liters. We do our calculation and we get 1.869 moles per liter. Now that's not our correct sig figs. We have 3 sig figs here, and we have 4 here, and 3 here. So we have to go to 3 significant figures, so that would become 1.87, and I'm going to write it as molar this time. And that is NH4Cl, or you could write it as 1.87 moles per liter of NH4Cl. Would anybody like to see that done in 2 steps rather than just in 1 line? Yes, okay. So let's do that same question in 2 steps. And I'm just going to write down our information. We had 250 milliliters and we had 25 grams of NH4Cl. So what I would do is I would start again and say I want to find the concentration of ammonium chloride, which means I want to find the moles of ammonium chloride per liter of solution. And I don't know those numbers yet, so what I will do is I will say I do know something about the ammonium chloride. I know the grams. So we will start by taking our 25. I want to find, whoops, sorry. moles of NH4Cl, and we're starting with 25 grams NH4Cl. So you want to cancel grams and find moles, and the molar mass was 53.5 grams per 1 mole. And we get 0.4673 moles. 0.4673 moles of NH4Cl. Even though we have only 3 sig figs and 3 sig figs, I'm going to keep an extra digit because when I put that back in my equation, I don't want to have a rounding error. So I'm just going to keep in mind that we have 3 sig figs, even though I've written 4 digits. So that number we can plug in up top where we need moles, 0.4673 moles NH4Cl. Now we wanted to have liters. So once again, there's 2 ways of converting milliliters into liters, 250 milliliters. You could either simply move the decimal place 3 places, 1, 2, 3, which would give us 0.2500 liters, or you could say my liters is 250 milliliters times, we want to cancel milliliters, and we want to find liters. There are 1,000 milliliters per 1 liter. So that gives us 0.2500 liters. Regardless, we pop that up into here, 0.2500 liters. Now we have our moles over our liters, and we should get the same number. And in fact, yes, we do. If we do that division, we still get 1.87 moles per liter, which is good because we should get the same answer as before. How are we feeling about finding molarity? Are we good? Okay, this is running a little bit long, but I would really like to get to using molarity as a conversion factor. If you're absolutely dying and you'd rather just watch the video later, I won't be offended. But stick with us if you would like to see it live. All right. So as Beatrice said before, our moles per liter is a, guess what? Conversion factor. And what it allows us to do is it allows us to go from moles of solute, whoops, back and forth to liters of solution. And in order to do that conversion, we'll use the molarity, which of course is the moles per liter. So, for example, what volume of 2.00 capital M, so that means molar, what volume of 2.00 molar H2SO4 sulfuric acid would contain 1.60 moles, this is 0, moles of H2SO4? SO4. So our conversion factor, the first thing you have to realize is that molarity is a conversion factor. It is sort of hidden, right? Because our conversion factor is actually 2.00 moles of H2SO4 per liter. So I would suggest that anytime you see molar, rewrite it as moles per liter so that you can see that it's a conversion factor. Rewrite it as moles per liter so you can see that it's a conversion factor. Why do I have a bracket there? That's awkward. Conversion factor. Es muy importante. So don't forget, whenever you see molar, rewrite it as moles per liter. So you see that conversion factor because that is our conversion factor. Now, if we go back to our question, we're looking and whenever we have a question where we're doing a conversion, we're going to have something that's unknown. In this case, our unknown is our volume. So our unknown is we don't know how many liters we have. And our known is 1.60 molar. That is our initial quantity. So our initial quantity is 1.60 moles, and we want to convert that into liters, and we're going to use our conversion factor to do that. So how that will look is we will have our unknown is equal to our initial quantity times our conversion factor. And if we just go back here really quickly, you can see that this is just a one-step process. If you're going from moles to liters, that is one step. So we'll only have one multiplication. So our initial quantity, 1.60 moles, times our conversion factor. We need to cancel moles, and we want to find liters. And so what is our moles per liter? This is the only place where people might go wrong here. They might see that and go, oh, 22.4, dang, got it. No, never when you have a solution, use 22.4. 22.4 is for gases only. So we'll just put a note down here. 22.4 liters per mole is for gases, whoops, only. Do not use it for solutions. So when you have solutions, you're not going to use 22.4. You will use instead the molarity, which will be given to you in the question. So we know from our question that there are 2.00 moles per 1 liter. We do our conversion, cancel out our moles, and we get, should have this calculated already, 0.800 liters. Okay, straightforward enough. We're going to do just one final example, and that's going to be to go the other way. So this question, we went from moles into liters. For our next and last example, we are going to go from liters into moles. So here's our question. How many moles of solid NaOH, sodium hydroxide, are required to produce 600 milliliters of 0.25 molar NaOH. So two things here. You should see, anytime you see milliliters, you should always rewrite your milliliters as liters. So you should always change that to liters. And anytime you see molar, you should always rewrite it as moles per liter. You're welcome. See you later. Rewrite as moles per liter. So let's do that. 600 milliliters. We're going to move our decimal place 1, 2, 3 places to the left. That becomes 0.6000 liters. And we'll rewrite our molarity as moles per liter. So that's going to become 0.25 moles NaOH per liter. So going back to our question, our initial quantity is the 600 milliliters. That's what we are given. The moles per liter is our conversion factor. So remember, molarity is a conversion factor. And our unknown is how many moles. So we're going to say our unknown is equal to the initial quantity times our conversion factor. Our unknown was the number of moles of NaOH. Our initial quantity is the 600 milliliters, which we have changed into 0.6000 liters. 0.6000 liters. And our conversion factor, we just have to figure out whether we want it right side up or upside down. We do want to cancel the liters, so it should go on the bottom. And we do want to have moles on the top because we've got moles there that we're looking for. And remember, do not use 22.4 because this is not a gas at STP. If you don't see gas in the question, if you don't see STP in the question, do not use 22.4. So we're going to use our 0.25. There are 0.25 moles of NaOH per liter. We do that, and we get 0.15 moles NaOH. And that is it. So you now know how to calculate molarity by doing a division, and you know how to use molarity as a conversion factor to go from either moles to liters or backwards from liters to moles. Are there any questions? Because if not, we're done. And you will find online an assignment on molarity that just gives you some practice problems. on this?